Okay. All right. I just posted this thing, midterm 2 topics. Let's take a look. This is what I wrote. This is the plan. So it'll be a lot like midterm 1, and yeah, okay. So I decided to have 2 midterms this quarter, and I hope that's okay. And I know I haven't finished grading midterm 1, and I apologize, and that's totally my bad. We'll try to get midterm 1 graded as soon as possible. I know I keep saying that, and I apologize. But yeah, we'll have midterm 2 on Wednesday, and it's open note, open book, and of course, you're not allowed to talk to each other, and we're gonna proctor it live via Zoom, and that's mostly to kind of just make sure you're working by yourself. And it'll be like midterm 1, because I think we did something similar for midterm 1, and I think it worked okay. And so anyway, we'll have it. There's 2 times, 9 a.m. and also at 6 p.m. And that's just to kind of accommodate people living in different time zones. And hopefully one of these time zones will work for you. And that will be that. Okay. And so basically, this one is going to be all pen and paper. And again, you can print out the exam and write on your printed papers. You can take a blank sheet of paper and write your answers on a blank sheet of paper, as long as you number your problems clearly. Or if you have some kind of tablet that's capable of doing it, you can write directly on the PDF itself. Okay. And if you print it out and something, you'll have to kind of scan the app using some kind of, or scan the pages using some kind of app. But I figure everybody did it for midterm 1, so hopefully should be fine. Okay, these are going to, as far as like what kind of questions you can put in a thing that's going to fit within this 90-minute period. This is what I've decided, and I hope this is fine. Okay, so 1, I'm going to set up a simple neural network. Okay, maybe 2 or 3 nodes in kind of your input layer, 2 nodes in your hidden layer, 1 or 2 nodes in your output layer or something. And you'll have, weight matrices and bias matrices. And just to kind of keep everything easy, the activation function is just going to be the identity function. So we're not going to bother plugging things into logistic, because that's just going to add a bunch of decimals and make your life harder. So we're just going to multiply things and move things along, and that's fine. Okay. I will provide you with some input matrix X, some, the values in your weight and bias matrices, and the actual values in the matrix T, the target values, and I'll also provide kind of your Y hat values. Okay, so if you take X and you forward feed it through all of this, you'll get the Y hat values, and I'll go ahead and do that. Okay. And so, so first, you'll just calculate your loss value. Simple enough, right? That's just the difference between Y hat and T. That's going to be given to you pretty much. You just basic arithmetic there. Okay. But what you're going to have to do is going to be the numeric gradient calculation. And I have to kind of figure out exactly how many things you've got to do here. But basically, you're going to kind of, add a small value, and it'll probably be something big, like 0.1. Small, but, comparatively large, because normally for numeric gradient calculation, you're adding something like 10 to the minus 5. But, at least for the purpose of the exam, you'll add probably like 0.1 or something. And you'll add it to some term, and you'll go through the calculations. You have to see how it gets propagated through the network, and then you'll measure what kind of change it has on the loss, and that will help you figure out what your numeric gradient is. Okay. All right, so that's numeric gradient calculation. So that should give you a sense of kind of how well, it requires that you understand how the forward feed works, and it'll require you to understand numeric gradient calculation. Okay, I'm not going to have you do like back propagation or something, just because it's already open note. So it's just going to end up being like you copy your homework answer down. So there's, I don't think it's a useful exercise to do back propagation on the midterm exam. Okay, this one, I don't know, potential to get a little bit harder, I guess, maybe. So one is there's going to be maximum likelihood estimation for some kind of univariate probability distribution. So, so you can think of some kind of probability distribution that depends on some parameter, like you know, a lambda parameter or a p parameter or something like that. Okay. And it'll be, you know, you can look at your lecture notes. So in lecture notes, I did maximum likelihood estimation for, you know, I think, you know, estimate the parameter of, you know, what proportion of marbles are red or something. And that was a Bernoulli example. Okay, it'll be something a little bit more complicated than Bernoulli, maybe. And then, so I'll provide, you know, whether it's a PDF or a PMF, okay, of the distribution. I'll provide that to you. And then I'll provide observations, okay? And then based on the observations and the PDF and PMF, you're gonna have to figure out what's the maximum likelihood estimate of the parameter based on the data. And here I'm looking for like the actual number, right? So like, it's not going to be the normal distribution, but like for the, you know, the maximum likelihood estimate for the normal distribution for the mean is just the mean of your sample. And I don't want you to give me X bar equals, you know, sum of X over N. I want you to tell me that it's going to be 3.5 because the numbers in my sample are 3.5 or something. Okay. And then, you know, please show your work for that. Okay. So, you know, you can go on Wikipedia. Distribution, right? And you can kind of, I'm going to pick something from here. Oh, wait, where did it go? Where's the list of probability distributions here? Go to, so yes, it will be independent samples. Okay, so something here where you've got some, this is actually a lot. Okay, but anyway, you can try out just a few of them. Maybe you check your 100B notes and stuff. Okay, and then we'll have an example for Fisher information, where you know, you kind of take the second derivative of the log likelihood, and you take the expected value of the second derivative of the log likelihood. You can again check your notes from lecture 5-2. So you know, I've referenced what kind of slides you should be on the lookout for. So if you go to lecture 5-2. So here's an example where we want the Fisher information, and so for the Bernoulli observation, this is kind of the Fisher information, and we take, you know, basically the second derivative, and we take the expected value of that, so will it be for one observation or for n observations? I have yet to decide that. I will keep in mind the time frame that you have, and it's not going to be something ridiculous, but you know, it's a little bit of work, right? Okay, and then we'll have a Bayes classifier example, and that's so we had an example like that in lecture, yep, like this. So in the Bayes classifier example, we were looking at these factory things, and we were trying to figure out, you know, what's the probability of it belonging to some class given something like that. Okay, so you can expect something kind of similar to this. It will, just to kind of keep things straightforward and simple, I'll maintain a Bernoulli binomial type of situation, much like the factories with the marbles. Okay, but you know, it'll obviously be different and things like that. So that will be doing a Bayes classifier. And then I'll have a handful of conceptual questions covering material from lecture. So it'll start with kind of, I think, when do we start neural networks? Like week 3. Okay, so it'll go kind of from covering stuff from neural networks through the Wednesday's topic on the naive Bayes classifier, right? So I won't cover, so today's stuff, which is on KNN, won't be on there, but up through naive Bayes classifier, so up through Wednesdays. So regular Bayes classifier and naive Bayes. So is the Bayes classifier the regular or the naive one? So the Bayes classifier is just, is not necessarily naive, okay? And then, but if you assume all of your predictor variables are independent of each other, then it becomes the naive Bayes classifier. But the Bayes classifier is just the classifier where you are predicting the classification based on what X values come in and the kind of the prior distribution of classes. So that's the Bayes classifier. And then if you have multiple X variables and you're assuming that they're independent of each other, then it's naive. If you're not going to assume that the X variables are independent, then it's just the regular Bayes classifier. Okay, any questions regarding the midterm exam, what it might look like, what you can expect? We're all good? Okay. All right, let me go ahead and give you your first view quiz answer for today, 6th week Friday. First view quiz answer is B. B as in bear. B as in bear. First view quiz answer. B. Okay, let's go ahead and get started with today's lecture. Today's lecture, I think, is pretty simple. It's just a bunch of pictures for, and we're going to take a look at the K nearest neighbors classification algorithm, K nearest neighbors. And so this is a simple algorithm, and it's useful. I would say it is not frequently used in production, okay? In production settings, if you have, especially if you have a situation where you have big data, K nearest neighbors is not popular just because it's so computationally expensive. But but it's a simple algorithm and it's useful. And if you have just a moderate amount of kind of training cases, it's quite popular. We have a question. It says, will we have to know the neural network demos that we showed? No. So basically, as far as what you can expect to see, it's just going to be this. I'm not going to put in outside stuff. Oh, I guess regarding the conceptual questions, yeah, I would say you should be familiar at least with the neural network for handwriting. Okay, I might have a question there. I won't ask questions about TensorFlow or things like that. Okay, so no questions about TensorFlow. Okay, or PyTorch or things like that. Yeah, actually, I didn't cover PyTorch, but that's the other popular neural network package. I won't ask questions about that. Okay, so the way K nearest neighbors goes, this is the entire algorithm. Okay, and this is what we would call a supervised learning because you need to have kind of target classifications that you want to predict, right? So you've got some training data. All of your training data has some kind of class label, okay? And basically, what you are going to do is you're going to take a new prediction, right? So a new value comes in, and this is how you're going to predict what class your new value belongs to, okay? So you have to measure the distance, and this is often the Euclidean distance from the test case, your new observation, to every single other point in the training data, okay? And so one thing about this is that because you're measuring the distance, the Euclidean distance to every single other point in the training data, k-nearest neighbors really only make sense if your predictor variables are numeric. If you have categorical predictor variables, it's difficult to measure distance. You need some kind of numeric. So if a person is located at 3, if an observation is located at 3 and the training data is located at 5, you can say, okay, that distance is 2, right? But if your new observation, let's say we're dealing with like colors of a car, right? Your new observation is a red car, and then your training cases are you have a white car and a silver car and a black car. Like, what is there a difference in distance? Is the distance the same or different? I don't know, right? So if you have a categorical variable, it's hard to do this. Okay. Also, if you have different variables of different types, your distance metrics, you might have to scale them or do something so that the distance metrics make a little bit more sense, right? So, for example, if you're talking about a person, you can look at the person's height and the person's weight, okay? And, the difference between a very tall person and a very short person might be like 18 inches, okay? And that would be, kind of a significant difference in height. 18 inches is a significant difference in height. But as far as weight goes, a difference of 18 pounds is not that significant, right? The difference between somebody who weighs, say, 170 and 188, it's not like a dramatic difference, right? And so, if we're talking about a significant difference in weight, it's going to be, different. And so you might have to say, well, maybe we need to kind of standardize these things or do something like that. Because if you kind of leave things as is, the measure of distance, might give just preference to just values that are much bigger or something like that. Okay. So anyway, those are things that you always have to kind of just think about. And that's always going to be the case, whether you're doing lasso or, some other kind of thing where you're, the size of the values matter, right? So anyway, but once you take that into account, you're going to measure the distance from the test case to every single other point in the training data, right? And depending, if you have a lot of training data, like if you have 1 million observations, then you've got to calculate 1 million distances. And so this can become very computationally expensive. And so for big data, k-nearest neighbors is not a favored solution just because there's so many things, okay? But anyway, once you have that, you're going to sort the resulting distances. You're going to say, all right, this one's the nearest and this one's the farthest. And then you're going to select the k observations with the smallest distances. And that's going to be the k nearest to neighbors. Okay, and that's where the name comes from, is that we're just picking some arbitrary k. We're going to pick the observations with the smallest distances. And then looking at those k nearest observations, you're going to say, all right, which class is represented the most? And, if we have like 5 observations and, 4 of them are red and 1 are blue, you're going to say, all right, the one with the highest representation, in this case, red, you're going to use that to make your prediction for the thing, okay? How should you pick k? This is always a question that people ask, and we don't have a great answer other than use cross-validation, okay? And the answer is going to differ for every kind of data set that you have. And so, in some data sets, your k should be, 3, and in other data sets, k equal to 7 or k equal to 20 might give you better performance. And so there's not a whole lot of like some kind of, you could dig into mathematical theory, but as far as kind of from a practical standpoint, we just kind of say, based on the data, we use different values of k for our training data, and using cross-validation, this value of k seems to perform the best, it had the most accurate predictions, and so we'll use this k going forward. Okay. Occasionally you'll run into a a situation where you run into ties as far as how many, which class is most represented, and there are no fast rules about how to resolve ties, and so there's a few different situations. And so, well, one, the simplest is if you have only two classes, like a red class and a blue class, and as long as you pick some odd number, k being an odd number, you won't have any ties. Okay, but as soon as you have more than two classes, it's going to be possible for there to be a tie. Okay, even if you have an odd number k, if you have k equal to 7, and if you have three classes, you could have 3 red, 3 blue, 1 yellow. Okay, and you'll have a tie for which class is most represented. So there's a few ways. How do you deal with this? One is you just say no class decided, and that's fine. You can just say unclassified. Okay. Another option is you can switch to the one nearest neighbor, and generally, as if your variables are continuous, there will not be a tie for which observation is the closest. It's possible. You could have two observations. You could have kind of you could have three observations that form like an equilateral triangle where, or yeah, I guess even a isosceles triangle or something, where you have two observations that have the same exact distance from your test case. That it's possible, but it's rare. Okay, but you can switch to the one nearest neighbor and say the nearest one is the group that we'll pick. You can just randomly pick among the groups that are tied, for the ones that are top tied, or you could say, among the ones that are top tied, we're going to select the group with the closest neighbor. And these are just different options. Okay. All right. Let's go ahead and just do a few examples, and we'll go through them. We'll probably, tonight's lecture will end a little bit early, but I think that's okay. It's a Friday. So, so here we're going to just generate some random values. And so this, I'm going to just show you two-dimensional examples, and it's going to feel silly, some of these steps, because our eyes can easily identify distances in 2 dimensions, okay? And so you might say, well, why do I have to calculate the distance from my point to every single other point in the data set? Well, the thing is once you get into higher dimensions, like in 8-dimensional space, it is no longer easy or readily apparent which observations are nearest, okay? In high-dimensional space, trying to figure out which observations are the distances in high-dimensional space is a lot more complex. So it's not easy. Okay, so anyway, I'm going to just go ahead and this is going to be our training data. Okay, so we have red observations and blue observations, and we're going to say, all right, this is it, and we're going to try out a test case. Okay, and so I'm going to put it in a test case right here, and we're going to say, all right, should this point be red or should this point be blue? Okay, so first we have to just kind of measure from our test case right here at 0, -1 to every single other data point in our training data. And again, it feels silly because we can just say, well, let's just look at the nearest ones. It's very obvious to us which points are closest. But again, in a high dimensional setting, it's not going to be obvious, just because, when you plot them, we don't have an effective way to plot high dimensional data. So, so you calculate the distance, and I've intentionally left out the code for doing this, just because that's part of your homework. So for homework 4, you're gonna have to write the code to do this, and it is possible to write some very efficient code or very concise code that will accomplish this task. Apparently, you can do it in as few as like 4 lines of code. If your solution takes like 20 lines of code, maybe even more, don't feel bad, okay? If you have like a for loop that goes through the whole thing, that's totally fine. I just want you to be able to think about how are you going to go from the idea to implementing it in some kind of solution. So that's your homework assignment this week. Okay. So anyway, you measure the distance to well, content from homework 4. So the only content from homework 4 that will be on the midterm is the stuff that I've listed here, which I think, so in homework 4, you have naive Bayes classifier, and that's going to be somewhat related to the Bayes classifier example. But it's also a little bit different. Homework 4 is a little bit more coding focused, and the midterm exam is a little bit more mathematical in nature. So, you know, hopefully by making you study for the midterm and making you write code in the homework, you'll get the full full experience for 102B. I don't know. Okay, so anyway, we calculate the distance, and then now we're going to say, all right, what are the nearest neighbors, right? So if you say k equals 1, this is the one nearest neighbor. I drew a circle to kind of indicate this is the one nearest neighbor to my test case. And in this case, we're going to pick red because red is the closest one. And if I pick k equal to 3, the 3 nearest neighbors, so this is the third closest one. I drew a circle to indicate that these are the 3 closest, and we can see we have 2 red and 1 blue. And so, you know, they each have a vote. The 2 reds win, and we would choose, we would classify this point as a red. Okay. Here, if I say k equals 5, as far as the 5 nearest neighbors go, 3 of them are blue and 2 are red. And so this one, if we had k equal to 5, our test case would be blue, would get classified as blue. And at k equal to 7, okay, this one almost made it, but it's apparently just a teeny bit farther than this observation. Okay, so with k equal to 7, we have 4 blue and 3 red. Okay, and so with k equal to 7, the blues win, and this would be also blue. Okay. Here's another case. If I did k equal, if my test case is at 1, 1, we're going to do this. We're going to calculate the distance to every single other point. And again, if I say k equals 1, red is the closest observation. So we're going to say this observation is red. With k equal to 3, I have 2 red and 1 blue. So this is going to get classified as red. With k equal to 5, I've got 3 red and 2 blue, so it still remains red. With k equal to 7, I have 4 red and 3 blue, and so it still remains red. Okay, and that kind of makes sense as far as this test case goes. We're still, it kind of makes sense that it's going to be red. Okay. Okay, question says, we say KNN is non-probabilistic, but couldn't you return a probability based on how many are from each class? And the answer is yes, you could. You could say, you could give, that is a true statement. You could do, based on your K, you can give a kind of a probabilistic class assignment as well. And so that's an option. There's actually KNN is built into R, and you just call KNN in R. And so all of this work, you know, that you're doing in your homework to write your own KNN, you're actually never going to use it in real life. You're going to, when you do KNN in production settings, you'll just use R as KNN setting, KNN function. But yes, in this case, we could say this point would get classified, you know, 67% red, 33% blue. This one would be 60% red, 40% blue. And you can do something like that, okay? With k equal to 7, you can do, I don't know what 4 over 7 is, 43%, maybe? No, 57%, I think, I don't know. Okay, all right, so what if I want to define some boundaries, boundary regions, okay? So this, we could say, well, where are things gonna get classified as red and where are things gonna get classified as blue based on my training data? Okay, and so all of this code, basically what it's doing, okay, is it is doing a whole bunch of test cases, okay? So I don't know if you can see this, but there's a grid of, you know, red and blue dots. And basically, I just ran the KNN algorithm. Okay, I just ran the KNN algorithm from R, okay, for every single one of these points. Okay, so we established some kind of grid, and I just ran the grid from -3 to 3 and -2.5 to 2. And I just created a big grid of points, and I ran KNN for every single kind of grid of points. And again, KNN in R, you can actually ask for the probability, and it will give you kind of a probability. And here I had said, well, where does the probability end up being 0.5? Okay, and so basically, if you take this for k equal to 1, you can say, where does a point get classified as blue or red? And so the computer went through and it calculated whether this dot is going to get classified as red or blue. And it did it for every single location. And then here it's drawn a boundary, basically between where the red and the blue line, where there are red dots and blue dots, to kind of indicate the boundary, right? And so it's not 100% smooth because I didn't do, you know, a super fine grid. It's a pretty fine grid, but it went through and it did KNN for every single one of these test cases and colored those test cases as red or blue. And this is kind of the boundary region that it created. Okay, so k equals 1 is almost always going to overfit. With k equal to 3, this is what ends up happening. Okay, so again, the same strategy applies. I just went through every single test case and I said, using k equal to 3, tell me, is this test case going to be blue or red? And it went through and it said, you know, for all of these points, this is going to get classified as blue and this is going to get classified as red. Okay, so this is what we get for k equal to 3. For k equal to 5, we get this. For k equal to 7, we get this. Okay, so what happens with, as you increase your k, any one individual point is going to have less influence. Okay, I don't want to say the border gets smoother, but the border is going to be less influenced by any one individual point, right? So with k equal to 1, this one observation, which is, you know, a bit of an outlier for, you know, as far as team red goes, you know, this one ended up kind of in the blue zone. This significantly drags kind of the boundary between red and blue way out over here. Okay, but you know, if I have k equal to 7, you know, the boundary almost ignores this entirely. Okay, it doesn't care that this point is out here. Okay, similarly for k equal to 5, you know, with k equal to 3, this dot does actually bring the boundary out a little bit in this direction. Okay, just because, you know, the kind of this red dot and this red dot kind of influence it, so that you know, points out here will say, you know, these points are actually get classified into the red. Okay, but once you get to k equal to 5, you know, these two red dots don't have enough power to kind of influence this region to be called blue. I mean, to be called red. So this region remains blue. Okay, whereas with k equal to 1, you know, points in this area will get called will be classified as red. Okay, but as k grows, the boundary is less influenced by any one point, but it looks a little bit more at kind of the overall, I don't know, trend, I guess, of points. Okay, so here's another example where you know, there's even more data and there's a little bit more mix of red and blue, a little bit more overlap. So we have, you know, some individual dots, you know, this blue dot and this blue dot, you know, way in the red territory, and this red dot way kind of out in blue, and this red dot way kind of out in blue. And so if you do k equal to 1, you get this. You get all of these kind of enclaves and exclaves of, you know, of whatever this is, right? So this is kind of like, it's kind of like that little piece of Russia that's in the middle of Europe, not in the middle of Europe, but like, where is it? Let's go to Europe here. What do you call this piece? This land here, right? What is this? Kaliningrad Oblast. Right. So this is Russia, but it's not connected to it's not like adjacent to the rest of Russia. So you end up getting with k equal to 1. And also like this Gibraltar, this is actually like this is owned by the United Kingdom, right? So I'm pretty sure Gibraltar belongs to the UK. It's like the most strategic location, but Spain doesn't have control over it. But it actually, it's about the British Overseas Territory, Gibraltar, whatever, self-governing British Overseas Territory. And, of course, Spain, they don't have control. They don't have the strategic location. The United Kingdom has claimed it. And well, anyway, so anyway, you get all of these kind of weird little exclaves if you have k equal to 1, right? So this blue dot is like, this whole territory belongs to blue, and this blue dot's like, yeah, this area belongs to blue, okay? And red goes, yeah, I'm on it too. This zone belongs to red. And this clearly is not going to be a good model overall, just because all of these things have so much, every one individual dot has, a little bit too much power and a little bit too much control. And so when you increase the K, okay, the boundary, you get, it still remains highly, it's not smooth, but, any one individual dot no longer has, powers to really influence it, okay? For k equal to 3, these two blue dots kind of work together somehow to form like an enclave or an exclave right here, okay? But, when you get to k equal to 5, at least the territory ends up being a little bit more contiguous, okay? And, it's only in like strange circumstances like this dot here ends up being still in red zone, but this is all blue and this is all red. And I think that makes a little bit more sense. And here, if I bump it all the way up to k equal to 20, we can see, the border just kind of makes a little bit more quote unquote sense. It's not exactly smooth, but you get kind of a boundary between red and blue that is not influenced by individual dots per se. All right. Okay, that's it for K nearest neighbors. It really comes down to just this first slide where you're going to just measure the distance. There are a few different algorithms that are based on K nearest neighbors. So you have like K medians and K medioids, which rather than using your Euclidean distance, they use either the Manhattan distance or different kind of ways of measuring distance. And so you have a few kind of derivatives or a few things that are similar to K nearest neighbors, but I would say this is overall, it's still widely used, but again, depending on how large your training data is, this step can become very computationally expensive. All right, let me give you your last two quiz answers for today. Last two view quiz answers are D and E. D as in dog, E as in elephant. D and E are your last two view quiz answers. Okay, and we'll call it a day here. So have a good weekend, and we'll see you guys on Monday.